Hello. So இன்னைக்கு வந்து நான் என்ன பண்ண போறேன்னா going back to linear algebra. Took like a couple of days off. Had a couple of thinking going on, and yeah, I'm gonna go back to linear algebra, and yeah, that's about it. I need to do sums too. Good thing is, I have everything here. I got my pen. Look at that. Look at that. Lovely. Lovely. I love Gilbert Strang. Okay. Talking so zesty. அப்போ இது எனக்கு புரியறதுக்கு ஃபஸ்ட்டு நான் இதை முடிச்சாகணும். அகெயின் போன இதில் வந்து I guess we covered like fully, if I'm not wrong.
This is what I
So இன்னைக்கு வந்து projections into subspaces. Again, இது ஃபுல்லாக பார்த்து முடிச்சுட்டு I need to go back to like review this thing, and I'm gonna do some again projection is like really connected to back propagation, I think, if I'm not wrong. I mean, projection in general, it's like really fuck. I don't know how I have this. Projection in generally. Oh, what am I doing? Fuck. My back hurts. In matrices is connected to a what is it connected to? Back propagation. Projection, yeah, are closely connected, so I better know what this shit means by the end of it. So what the hell? The fuck am I looking at? I didn't learn this one. So the formula, just to do like a little recap, நம்ம அன்னைக்கு பார்த்தது என்னன்னா permutation is equal to ax y z ax, I mean, let's say in a 2D permutation, right? Ax y is equal to ax ay, meaning this is a projection, right? This is about projection. This is not really about transformation, right? We need to understand transformation. This is not equal to this, but for projection, ax ay is equal to ayx. It doesn't matter how okay, let me actually get like an actual thing going on. Let's say we are taking this matrix, this vector, and we're transforming இதை வந்து இப்படி திருப்பி ஓகே இப்படி திருப்பி இன்வெர்ட் பண்ணுறோம், அப்சைட் டவுனாக திருப்புறோம். ஓகே, இது அப்சைட் டவுனாக திருப்பி லெஃப்ட் சைட் ரைட்டாக திருப்புறோம். ஓகே, ஃபர்ஸ்ட் ஸ்டெப் வில் பி this is step number 1, step number 2, right? இப்போ இதை நம்ம அப்படியே இன்னொன்று ஆர்டரில் போட்டோன்னா step number 2, step number 1. So with this, what does it actually mean? It doesn't really like the projection still remains the same. That's the underlying idea behind all this. Okay. Yeah, transpose is really important. And I forgot to say this. I looked at some copyright laws, and I was able to like stream some of this stuff, so I will be going over the entirety of the book, hopefully. And luckily, we covered this thing. Okay, this thing, this thing, this thing. I mean, I covered it like before actually start streaming, right? இதை வெக்டர் ஸ்பேசஸ் கொஞ்சம் கவர் பண்ணோம், லினியர் இண்டிபெண்டன்ஸை கொஞ்சம் கவர் பண்ணியிருந்தேன், பேசிஸ் கொஞ்சம் கவர் பண்ணியிருந்தேன் ஆல்ரெடி, linear mapping, all of this shit I haven't done, and analytical geometry, like never done. So if we go back, matrix decomposition and trace, again this is a little bit more advanced. Eigenvectors கொஞ்சோண்டு தெரியும், but other than that all of this is like pretty high level and never actually like done anything with it. Ow. Apple vector calculus, first time hearing that. So again, this is the proper order that I should be like learning. But regardless, I'm gonna like do I'm gonna finish all the propagations, right, from Gilbert Strang. That's the website, by the way. I'm gonna finish all of this shit, even like this thing over here. I'm gonna finish till this one. This is all like theory shit anyway. And fuck. This shit is like really important. And obviously Markov's matrices is like an underlying thing for the Markov chain, which basically is like a theory of everything. So that's the game plan. I'm gonna skip some of the stuff and hopefully come back whenever I need. You know what I mean? I'm gonna, for now, for the next couple of streams, it's just gonna be this one. And I'm going to switch back to the book. I'm going to follow the book and come back to Gilbert Strang whenever I need it. Okay, that was a long-headed, long-winded explanation of what I'm going to do. Let's actually start doing it. Okay.
See what the geometry looks like when I'm in the two dimensions. I'd like to find the point along this line. So that line through A is a one-dimensional subspace. So I'm starting with one dimension. I'd like to find the point on that line closest to B. Can I just take that problem first, and then I'll explain why I want to do it and why I want to project on other subspaces. So where's the point closest to B that's on that line? It's somewhere there. And let me connect that. And
so this
what's
is
the whole point of my picture now?
This kind of coincides with cross product. And yeah, again, if the degree, if I remember correctly, so let's say in the vector, obviously you can project on here and nothing happens, right? இது வந்து ஒரு straight down ஆக இருக்கணும், இல்லை let's say இந்த directionல project பண்ணலாம், எப்படியான அது project பண்ணலாம். Okay, so again in this case it's like 90 degree. That's what we're doing. So let's say in the Mother matrix, I mean in the Mother and how do you actually project? So you just take this shit over here and you project this way. I think like it Papo, another one Papo.
Where does orthogonality come into this picture? The whole point is that this best point, that's the projected B of B onto the line. Where's orthogonality? It's the fact that that's the right angle. But the error. This is like how much I'm wrong about. This is the difference between B and P. The whole point is that's perpendicular to A. That's got to give us the equation. That's got to tell us, that's the one track we know, that's got to tell us where that projected is. Let me also say, look, I've drawn a triangle there. So if we were doing trigonometry, we would have angles theta, and distances that would involve sine theta and cos theta, that leads to lousy formulas compared to linear algebra. The formula that we want comes out.
Like a bigger idea that I'm having is I'm gonna do some linear algebra course. I haven't even like fucking learned linear algebra. I'm thinking of making a course. It's funny. I'm gonna learn the Manimum Python library. That's what Gilbert Strang. Gilbert Strang. 3 blue 1 brown use பண்ணிட்டு இருந்தான். So again, as soon as I learn pretty much like the entire thing, I'm gonna release a course, so to speak, in my YouTube channel. Hopefully, same YouTube channel. I'm not gonna இடத்துல போயிட்டு release பண்ண நான் யோசிக்கல. I mean, I just find it like funny because I think I could like make a lot of niche, if that's the word, niche content for a lot of people. I think I'm like, yeah, let's see. Let's just, I don't know.
What do we know? We know that P, this projection, is...
Okay, E is equal to B minus P? What the fuck? Where did that come from? What the... Bro, I'm in my head for like 2 seconds. I forget everything.
The error. This is like how much I'm wrong by. This is the difference between B and P. The whole point is that's perpendicular to A. That's got to give us the equation. That's got to tell us, that's the one fact we know, that's got to tell us where that projection is. Let me also say, look, I've drawn a triangle there. So if we were doing trigonometry, we would do, we would have angles theta and distances that would involve sine theta and cos theta. That leads to lousy formulas compared to linear algebra. The formula that we want comes out nicely. And what do we know? We know that E, this projection, is some multiple of A, right? It's on that line. So we know it's in that one-dimensional subspace. It's some multiple, let me call that multiple X, of A. So really it's that number X I'd like to find. So this is going to be simple in 1D, so let's just carry it through and then see how it goes in high dimension. Okay, the key fact is, so the key to everything is that perpendicular. The fact that A is perpendicular to E, which is B minus A x A. I don't care about that. That equals 0. You see that as a central equation? That's saying that this A is perpendicular to this correction. That's going to tell us what X is.
Again, this is like really building off the stuff we learned the other day, which is, let's refresh. Let's not like think we're better than refreshing. Permutation. Fucking projection. Bro, I love this fucking site. Okay, projection is a special matrix P. Projection is a matrix, okay. That when you multiply any vector x, any vector meaning sunlight, right? In our example, the sunlight, by P drops orthogonally onto some subspace S, okay. S. Two of the more common cases, the projection to one-dimensional space, U is equal to R is equal to N. If it's a one-dimensional space, then this is the formula. I don't know how they got it, but I'm gonna trust my friends in the government and satisfies. Okay, projection onto some column space, fully ranked. Okay, we get it, bro. We get it. What is P? Oh, did I fuck anything up? I hate when that happens. Did it like change it? Fuck you. Okay. Does capital P is equal to XA? What does that mean? It's my hotkeys, My hotkeys always fuck me up. Okay, let's see. The equation is just shorthand for saying P is obtained by multiplying A on the left. Okay, what does it mean? X is a scalar. Here's here's two concrete projection illustration. One with a tree casting a shadow on the ground, and another one is a stick casting a shadow onto a line. Sun coming from a fixed direction. Tree. Shadow on horizontal plane. Think of points in space as vectors. Okay, whatever. Oh, can you guys see my nipple? It's cool, it's whatever. Whatever.
Simplify that and out will come in.
Okay, okay, I need to draw some lines. Okay, இது வந்து இங்க expressed ஆயிடுச்சு. Okay, E, what the fuck is E? Where does it come from? Did he like E is the perpendicular line? Okay, so A transpose E is equal to 0. What?
Okay, so if I simplify that, let's see, I'll move one term to one side, the other term will be on the other side. It looks to me like X times A transpose A is equal to A transpose B.
Okay, how did you get that?
A transpose B.
I'll try to do that. It's going to be a little bit more satisfying when I do it. Oh, it's cold actually. 1 second. For God's sake. You're gonna get a close foot reveal. All of the gooners are gonna love this one. Look at that. Look at that. Nice feet. Okay, let's not get distracted. It's cold. It's kind of cold here. So what is he coming to say? He's coming to say, what is A transpose E is equal to 0? What does it actually mean? A is just... Okay, let's... So we have ATP minus AXT. A is equal to 0. எடுத்து அங்க போட்டா ATB is equal to X ATA. I mean this shouldn't like change. That's the main thing. The multiplication order shouldn't change. But the interesting thing is it gets kinda in the middle. That's the interesting thing. Why? I mean, X really doesn't matter, right? Maybe it matters, I don't know.
That one term, A transpose A is the other. So right away, here's my A transpose A, but it's just a number now. And I divide by it, and I get the answer. X is A transpose B over A transpose A. And P, the projection I wanted, is that's the right multiple. That's got a cosine theta built in, but we don't need to look at angles. We've just got vectors here. And the projection is P is A times that X. Or X times that A. But eventually I'm going to want that X coming on the right-hand side. So you see that I've got two of the three formulas already right here. I've got the equation, that's the equation that leads me to the answer. Here's the answer for x, and here's the projection. Okay, can I add just one more thing to this one-dimensional problem? One more, like,
Yep.
lift it up into...
Okay, this is a one-dimensional thing. Oh, it's two-dimensional though.
In the matrix. Here's the last thing I want to do, but don't forget those points. A transpose B over A transpose A. Actually, let's look at that for a moment, please. Suppose, and A, well then, let me take this next step. So P is A times X. So can I write that then? P is A times
Okay,
A transpose
okay.
B over A transpose A.
Okay.
That's our projection. Can I ask a couple of questions about it, just while we digest that formula? Suppose B is double. Suppose I change B to 2B. What happens to the projection? So suppose instead of that vector B that I drew on the board, make it 2B, twice as long. What's the projection now? It's double 2, right? It's going to be twice as far. If B goes twice as far, the projection will go twice as far. And you see it there. If I put in an extra factor 2, then P's got that factor 2. Now what about if I double A? What if I double the vector A that I'm projecting onto?
Oh, okay. E is just some number. Wait, what? B minus P. What is P? How did you come to this formula? What the fuck? I wish I can just... No. Okay, A transpose okay, just show me the thing, bro. A transpose B minus AX. Is that what it is equal to 0? XA. Bro, what the fuck? What am I even like reading? What am I reading? The fuck? It's exactly orthogonal conditional that says vector B is equal to XA is perpendicular to orthogonal vector. Okay, let me write it down. Too much like words, bro. Can you can you just show? You know what I mean? So, fuck, look at that. Retarded. Who even like goes for this shit? Who wants to annotate with this shit? You know what I mean? You're fucking retarded. Let's take another 2 shit. B and A. We have same thing. Is B is projecting onto a span of B. Suppose it's a non-vector and you want to find the best approximation of multiple of that. Comes to closer to B. In other words, you seek a scalar x so that the difference residue is small as possible. Whatever that means. Formally, you minimize the function. Okay. Take the derivative. Holy fuck. Holy fuck. What are we doing here? What are we doing here, bro? The fuck are we doing here? Where does even x come from? R is equal to, in other words, the scalar is equal to is difference between. What is x? What is r? What is all of this shit? Like I haven't like Did he like say it in the previous lecture that I missed to catch it? Like, what is all this shit? Like, what is R? Summary. No, he did not say what R is. So, what is going on, Mr. Gilbert? I thought I liked you. What the fuck? Okay, anyway, let's continue.
But I'm just the line between. If I double A or I take minus.
Yeah, whatever. Like, I'll just like finish the equation. So we have this P is equal to X A, and we have E is equal to B minus A, and we have, for some reason, A transpose B minus E is equal to 0. Stupid shit. And we have, yeah, it's actually, math is actually fun. How about that? This is actually fun, but everything else can fuck off. Okay, and what else? I'm missing something. I need to substitute the P. No? P is done. Okay, I just have to multiply, I guess. I still don't understand why the A transpose comes before, but it is what it is. It is what it is. And what are we representing? Are we doing X? Yep. X is equal to, you can't really cancel it for some reason, so we're gonna put this shit on P. That's what he did. Okay. I still don't understand this. What is I fucked it up.
Say, it's still that same line. The projection's still in the same place. And of course, if I double A, I get a 4 up above, and I get a 4 extra 4 below. They cancel out, and the projection is the same. Okay. So really, this, I want to look at this as the projection is, there's a matrix here. The projection is carried out by some matrix that I'm going to call the projection matrix. And in other words, the projection is some matrix that acts on this guy B and produces the projection. The projection P is the projection matrix acting on whatever the input is. The input is B, the projection matrix is P. Okay, actually you can tell me right away what this projection matrix is. So this is a pretty interesting matrix. What matrix is multiplying B?
Oh, that's actually neat. That's actually neat. So projection matrix is basically this shit. And this could be written as A is equal to AT. Whoa, mind blown. Mind blown. Or you could write it A, AT, whatever. I mean, the order matters, I think. Bro, that was so tough. That was actually tough. If it's orthogonal, like what the fuck? I don't understand it. Let's go.
So from my formula, I see what P is. P, the projection matrix, is, what is it? I see A transpose above, and I see A transpose A below. And those don't cancel. That's not one. right? That's a matrix. Because down here, the A transpose A, that's just a number. A transpose A, that's the length of A squared. And up above is a column times a row. Column times a row is a matrix. So this is a full-scale n by n matrix if I'm in n dimensions. And it's kind of an interesting one. And it's the one which, if I multiply by b, then I get this. You see, once again, I'm putting parentheses in different places. I'm putting the parentheses.
Whoa, that's even like cooler. Check out this. So the idea is, since this is not equal, right? Yeah, this is not equal. You can't really cancel it. And I don't think you can cancel in matrix anyway. So the conclusion is, so the bottom one, this the bottom one will be a full matrix, will be a, right? And this will be a different matrix. Let's say A1, A2, or something like that, because the order matters again. This one. Okay. Okay, bro.
Right there. I'm saying, okay, that's really the matrix that produces this projection. Okay. Now, tell me, all right, what are the properties of that matrix? I'm just using letters here, A and B. I could put in numbers, but I think for once it's clearer with letters because all formulas are simple. A transpose B over A transpose A. That's the number that multiplies the A. And then I see, wait a minute, there's a matrix here. And what's the rank of that matrix, by the way? What's the rank of that?
Should be like a symmetric square matrix. I mean, not a symmetric, a square matrix. The rank, how do I determine the rank? Every I don't know. Tell.
Let me just ask you about that matrix, which looks a little strange. A transpose over this number, but well, I could ask you which column space. Yeah, let me ask you which column space. So what's the column space of the matrix? It's if you multiply that matrix by anything, you always get in the column space, right? The column space of the matrix is when you multiply any vector by that matrix, any vector b, by the matrix, you always land in the column space. That's the column space equation. Now, what space do we always land in? What's the column space of, what's the result when I multiply this any vector b by my matrix? So at p top p, where am I? I'm on that line, right? The column space, so here are facts about this matrix. The column space of p, of this projected matrix, is the line through A. And the rank of this matrix is, you can all say that once, 1. Right, the rank is 1. This is a rank 1 matrix, actually, which is exactly the form that we're familiar with rank 1 matrix, with a rank 1 matrix. A column times a row. As a rank 1 matrix, that column is the basis for the column. Just one dimension. Okay, so I know that much about the matrix, but now there are two more facts about the matrix that I want to notice. First of all, is the matrix symmetric? That's a natural question for matrices. And the answer is yes. If I take the transpose of this, there's a number down there. The transpose of A transpose is A transpose. So P is symmetric. P transpose equals P. So that's a P property, that the projected matrix is symmetric. One more property now, and this is the real one. What happens if I do the projection twice? So I'm looking for something, some information about P.
Same thing.
But just give me in terms of that picture. In terms of
Shook,
my picture,
shook.
I take
Shook, shook, shook.
I
Same
multiply
thing.
by my projection matrix, and that puts me there. So this is P, P. And now I project again. What happens now? What happens when I apply the projection matrix a second time to this? So I'm applying it once, brings me here, and the second time brings me, I stay put. Right? The projection, for a point on this line, the projection is right where it is. The projection is the same point. So that means that if I project twice, I get the same answer as I did in the first projection. So those are the two properties that tell me I'm looking at a projection matrix. It's symmetric, and its square is itself. Because if I project the second time, that's the same result as the first projection. Okay, so that, and then here's the exact formula.
That makes sense.
Line to A, then I know what P is. So you see that I have all the pieces here for projection.
Yep.
Now, and those, please remember those. So there are three formulas to remember. The formula for X, the formula for P, which is the AX, and then the formula for capital P, which is the matrix. Good, good. Okay. Now, I want to move to more dimensions. So we're going to have three formulas again, but you'll have to, they'll be a little different because we won't have a single line, but a plane or a three-dimensional or a n-dimensional subplane. Okay. So now I'll move to the next question. Maybe I'll say first. I'll say first why I want this projection, and then we'll figure out what it is. We'll go completely parallel there, and then we'll move. Okay. Why do I want this projection? Well, so why projection?
Jing jing.
Because as I mentioned last time, this new chapter deals with equations.
Shing. That's why.
May really my problem. That I'm given a bunch of equations, probably too many equations, more equations than unknown, and I can't solve them. Okay, so what do? I solve the closest problem that I can solve. And what's the closest? Well, AX will always be in the column space of A. That's my problem. My problem is AX has to be in the column space, and B is probably not in the column. So I change B to what? I choose the closest vector in the column space. So I'll solve AX equals P instead. That one I can do. Where P is, this is the projection of B onto the column space. That's why I want to be able to do this, because I have to find a solution here, and I'm going to put a little hat there to indicate that it's not the x that doesn't exist. It's the x hat that's possible. So I must be able to figure out what's the good projection there. What's the good right-hand side that is in the column space, that's as close as possible to B, and then I know what to do. Okay, so now I've got that problem. So that's why I have a problem again. But now let me say I'm in 3 dimensions. So I have a plane, maybe, for example, and I have a vector B that's not in the plane. And I want to project B down into the plane.
So, என்ன மாதிரி ஒரு எக்ஸாம்பிள் எடுக்கலாம்? It's not in the line ங்கிறான் அப்படின்னா bro, what the fuck is this drawing? என்ன சொல்ல வரீங்க Gilbert Strang? I love you so much, but what the fuck is this? Is it like through it? I guess the idea is, I mean, if I draw, it's even fucking worse. But okay, என்ன சொல்ல வரான்னு கேட்போம். சொல்லுங்க சார். சொல்லுங்க.
So there's my question. How do I proceed?
Okay, I can't understand it. இங்கே ஒரு பிளெயின் இருக்கு. இந்த பிளெயினுக்கு இப்படி போகுது. பட் when I ப்ரொஜெக்ட் பண்ணும்போது இப்படி. ஸோ என்ன சொல்ல வரீங்க சார்? Maybe it's like the same origin or whatever too.
Really what I'm looking for is a nice formula, and I'm counting on linear algebra, so just come out right. A nice formula for the projection of B into the plane, the nearest point. So this, again, a right angle is going to be crucial. Okay, now first of all, I've got to say, what is that plane? To get a formula, I have to tell you what the plane is. How am I going to tell you a plane? I'll tell you a basis for the plane. I'll tell you two vectors, A1 and A2, that give you a basis for the plane. So let's say there's an A1, and here's a vector A2. They don't have to be perpendicular, but they better be independent. Because then that tells me the plane. The plane is the plane of A1 and A2. And actually, going back to this connection, this plane is a column space. It's the column space of what matrix? What matrix? So how do I connect the two questions? I'm thinking, how do I project onto a plane? And I want to get a matrix in here. Everything's cleaner if I write it in terms of a matrix. So what matrix has that column space? Well, of course, it's just the matrix that has A1 in the first column and A2 in the second column. Right? Let's be sure we've got the question before we get to the answer. So I'm looking for, again, I'm given a matrix A with 2 columns. And really, I'm ready, once I get to 2, I'm ready for n. So it could be 2 columns, it could be n columns. I'll write the answer in terms of the matrix A. And the point will be, those 2 columns describe the plane, they describe the column space, and I want to project. Okay, and I'm given a vector B that's probably not in the column space. Of course, if B is in the column space, my projection is simple, it's just B. But most likely, I have an error E, this B minus P part, which is probably not zero. Okay, but the beauty is that I know from geometry, or I could get it from calculus, or I could get it from linear algebra, that this vector, this is the part of B that's perpendicular to the plane. That E is perpendicular to the plane. Your intuition is saying that that's the crucial fact, that's going to give us the answer. Okay, so that's the problem. Now for the answer. So this is a lecture that's really like moving along. I'm just putting that problem up there and asking you what combination. Now, yeah, so what is P? What is this projection P? This projection P is some multiple of these basis, right? Some multiple of the columns.
Yeah.
But I don't like writing out x1, a1 plus x2, a2. I would rather write that as a x. Well, actually, of course, I'm really doing everything right. I just put a little hat on. Remember that this x, those are the numbers, and I'll put a hat way back there.
Oh, that's the same formula, okay.
Right? So this is the projection P. P is ax bar, and I'm looking for x bar. So that's what I want in the equation. So now I've got hold of the problem. The problem is find the right combination of the columns so that the error vector is perpendicular to the plane. Now, let me turn that into an equation. So I'll erase the board and just turn what we've just done into an equation. So I'll write again the main point. The projection is a x bar, x hat, and And our problem is find X hat. And
What would the rank be? Who knows? The fuck?
and the key is that
I don't know. Rank, find X. Okay. Well, okay, it's not a matrix. Duh. But what am I
B
doing?
minus AX hat, that's the error. This is the E, is perpendicular.
Oh, that's the error. Okay. Error is B minus P. B minus projection. That will be the error. Okay. So B is here. P is here. So yeah, that will be the error. If instead of it being like a right angle triangle, if it's like here or something, that will be the error. I don't know. Don't know. Oh, what did I do?
Done into an equation. Perpendicular means, well, what am I looking for? I'm looking for two equations now. I've got an x1 and an x2. And I'll get two equations because, so this thing E is perpendicular to the plane.
Mm-hmm.
So what does that mean? I guess it means it's perpendicular to A1 and also to A2.
Yeah.
Right? Those are two vectors in the plane. And the things that are perpendicular to the plane are perpendicular to A1 and A2. This guy then is perpendicular to the plane, so it's perpendicular to that vector and that vector. It's perpendicular to that, of course, but it's perpendicular to everything in the plane. And the plane is really told me by A1 and A2. So really I have the equation A1 transpose B minus AX is 0, and also A2 transpose B minus AX is 0. Those are my two.
Okay, perpendicular meaning. Yeah, perpendicular. That's like a formula. So the formula is A is equal to minus the error. B minus the vector projecting minus the error. Okay, that will be the 0 in the first one because that's like A1, A2. Okay, I understand the question. Makes sense. Kinda. I need to like solve a problem though.
But I want those in matrix form. I want to put those two equations
Matrix
together.
form? Wait. Should I expand it? Okay, should I? Okay, he needs it in a P is equal to this kind of thing. P is equal to B by what? No. What am I doing? P is equal to that like big ass equation, isn't it? Oh, does he want the x? X is equal to what is x is equal to? I was thinking about a fucking girl. I don't know. How do I do it? Okay, let me just like put all of this shit in here so that I can get some ideas. X at, we have, do we have to minus it? Okay, no, it doesn't matter. What am I looking at? Okay, what's next? What am I gonna... What? What? No, 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 no. It's A transpose 1. What can I do with this? It's gonna be, the next one is gonna be same as this one. It's gonna be B is equal to A transpose. Fuck, what am I doing? Back. It's gonna be like B A transpose 2. So what am I gonna find? So X, oh, the same thing is X, okay. So this is equal to this. Okay, let me like try to abbreviate it. So B is equal to and I'm supposed to find what? A? Okay, I think some of it can cancel out. Can I cancel it? Let's just try. I don't know. Oh, can you? Can you cancel it? I think you can. The matrix A into A inverse is identity matrix, right? So yeah, I think I can cancel it. I think I can cancel it, yeah. B vector, let's cancel it. I don't know. Let's see. Oh. What am I going to do with that? Is it just A, T? I mean, that's a cool looking stuff, but I don't know what it means. I need to actually go and rewatch the transpose video.
And it just comes out right. Look at the matrix transpose. Put A1 transpose as its first row. A2 transpose as its second row. That multiplies this B minus AX.
Mm-hmm.
And gives me the 0. And the
Oh, okay, I couldn't even do that. Okay.
And you see that this is one way to come up with this equation. So the equation I'm coming up with is A transpose B minus AX hat is this. Okay. That's my equation. All right.
Okay, I don't have to cancel it, so yeah, I think what I came up with it is perfectly. Bro, that's what I was trying to say. Like, what the fuck? He's gaslighting me.
For a moment before I solve it and just think about it. First of all, you see that equation back in the very first problem I solved on a line. What was the on a line? The matrix A only had one column. It was just little a. So in the first problem I solved, projecting on a line, this for capital A, you just change that to little a, and you have the same equation that we solved before. A transpose.
That's just a row space.
Okay. Now a second.
It's in the column space.
I would like to, since I know about these 4 subspaces, I would like to get them into this. So let me ask the question. What subspace is this thing in? Which of the 4 subspaces is that error vector E? This is nothing but E. This is this guy coming down down perpendicular to the plane. What subspace is E in from this equation?
It should be in the plane. I don't know.
Well, the equation is saying A transpose E is 0. So I'm learning here that E is in the null space of A transpose. Right? That's my equation. And now I just want to see A, of course, that was right. Because things that are in the null space of A transpose, what do we know about the null space of A transpose? So the last lecture gave us the sort of the geometry of these subspaces and the orthogonality of them. And you remember what it was? What on the right side of our big figure, we always have the null space of A transpose and the column space of A and their orthogonal. So E in the null space of A transpose is saying E is perpendicular to the column space of A. Yes.
Yeah. Yeah.
I just feel.
Whoa, I kind of get it. Yeah, I get it.
Hey,
Kinda.
everything came out right.
So the whole thing, என்ன சொல்ல வர்றாருன்னா, that's the whole debacle with this thing, right? Not transpose, column space, row space, and it's orthogonal. So what he's trying to say is E is in the null space because of the formula. E is in the null space, right? And null space is orthogonal. So E is orthogonal, or in other words, perpendicular.
The equation that I struggle to find for E really says what I want. That the error E is perpendicular to the column. Just so. And from our four fundamental subspaces, we knew that that is the same as that. To say E is in the null space of A transpose is E is perpendicular to the column. Okay, so we got this equation, now let's just solve it. All right, let me just rewrite it as A transpose A X hat equals A transpose B. That's our equation. That gives us A. And
Cool.
allow me to keep remembering the one-dimensional case. The one-dimensional case, this was little a. So this was just a number. Little a transpose A was just a vector, row times a column of numbers. And this was a number. And X was the ratio of those numbers. But now we've got matrix. This was
Okay. Bro, I get it. Okay, so the way he taught us was like from one-dimensional, two-dimensional, and three-dimensional would be similar to this. Very similar to this. I mean, it's the same thing, right? A could be like a 4x4 matrix.
Oh, yeah. A
3 by
transpose
3
A is n by
matrix,
n
whatever.
Okay, so can I move to the next board for the solution? Okay, this is the key equation. Now I'm ready for the formulas that we have to remember. What's that cat? What's the projection? What's the projection matrix? Those are my three questions that we answered in the 1D case, and now we're ready for in the n dimension. So what is that cat? Well, what can I say but A transpose A inverse, A transpose B. So, that's the solution to our
Yeah.
What's the projection? That's more interesting. What's the projection? Projection is A.
Projection. Yo, projection, we have like a formula, right? A is
That's how
equal
I
to
got into the picture in the first place.
XA.
That was the
I mean, yeah.
combination of columns, and I had to look for those numbers, and now I found them. Was
AXA.
the combination of the columns of A that gave me the
AX.
projection. Okay, so
Hat.
now I know what this guy is. So I multiply by A transpose A inverse A transpose B. That's looking a little messy, but it's not bad. That combination is our like magic combination. This is the thing, which is like
Identity
what was it
matrix.
in combination?
No?
What was it? We must have had this thing way back at the beginning of the lecture. What did we? Oh, that A was just a column, so it was little a transpose over A transpose A, right? That's what it was. It's 1D.
Yeah.
You see what happened in more dimensions. I'm not allowed to just divide because I don't have a number. I have to put inverse because I have an n by n matrix. But same formula. And now tell me what's the projection matrix? What matrix is multiplying B to give the projection? Right there.
What?
What matrix is multiplying B to give the projection? Right there. That's there. I even already underlined it by accident.
Yeah.
The projection matrix, which I use capital P, is this. This is that. So I write it again. A times A transpose.
Bro, that's
inverse
good.
Times A transpose.
I feel like I've learned a lot of things, but I haven't.
Now, if you'll bear with me, I'll think about what have I done? I got this one. Now, the first thing that occurs to me is something bad. Look, why don't I just, here's a product of two matrices and I want it inverse. Why don't I just use the formula I know for the inverse of a product and say, okay, that's A inverse times A transpose inverse. What will happen if I do that? What will happen if I say, hey, this is A inverse times A transpose inverse, then shall I do it? It's going to go on videotape if I do it. And I go, all right, I'll put it there. It's like, don't take the videotape quite so carefully. Okay, so if I put that thing, it would be A inverse, A transpose, A transpose, and what's that? That's the identity. But what's going on? So, see, my question is, somehow, I did something wrong. That wasn't allowed. And why is that? Because A is not a square matrix. A is not a square matrix. It doesn't have an inverse. So I have to leave it that way. This is not okay. If A was a square invertible matrix, then I couldn't complain. Yeah, I'll think about that case. But my main case, the whole reason I'm doing all this, is that A is this matrix that has too many rows. It's just got a couple of columns, like A1 and A2. But lots of rows. Not square. And if it's not square, this A transpose A is square, but I can't pull it apart like this. So I'm not allowed to do this pull apart, except if A was square. Now, if A is square, what's going on if A is a square matrix? A nice square invertible matrix. What's up with that? What's with that case? the formula ought to work very quickly. If A is a nice square invertible matrix, what's its column space? So it's a nice n by n invertible, everything great matrix. What's its column space? The whole of Rn. So what's the projection matrix if I'm projecting under the whole space? It's the identity, right? If I'm projecting B under the whole space, not just onto a plane, but onto all of 3D, then B is already in the column space. The projection is the identity, and this gives me the correct formula. B is up. But if I'm projecting onto a subspace, then I can't split those apart, and I have to stay with that formula. Okay. And what can I say? So I remember this formula for 1D, and that's what it looks like in end of it. And what are the properties that I expected for any projection matrix, and I still expect for this one? That matrix should be symmetric, and it is. P transpose is P. Because if I transpose this guy's symmetric, and its inverse is symmetric, and if I transpose this one, when I transpose it, will pop up there, it becomes A. The A transpose will pop up here, and I'm back to B. And do we dare try the other property, which is P squared?
P square.
It's got to be right. But we know geometrically that the first projection pops us onto the column space, and the second one leaves us where we are. So I expect that if I multiply by, let me do it, if I multiply by another P, so there's another A, eight A's in a row. So how do I see that multiply together? So when that's okay, we really have got now all the points. X hat, the projection P, and the projection matrix at P. And now my job is to use. Okay, so when would I...
Bro, that's actually fine. You see here. So this turns into a identity matrix, and this turns into an identity matrix, and gets cancelled out. Fucking neat. Neat.
When would I have a bunch of equations? Too many equations, and yet I want the best thing. And the most important example, most common example, is if I have points. Well, here's the application. These squares. Fitting by a line. Okay. So I'll start this application today, and there's more in it than I can do in this same lecture. So that will give me a chance to recap the formulas, and there they are, and recap the ideas. So let me start the problem today. I'm given a bunch of data, and they lie close to a line, but not close.
Whoa, we get into the application bit of things. I need to take a piss though. This is like really similar to linear algebra, which is, I mean, linear regression is what I meant to say. Bro, I'm actually in... yeah, I need a quick piss break. I'll be back. No noise. Being a good little boy. Being a good little boy.
1, 2, and 3. I have
Okay.
1 and 2 and 2 again. So my data points are, this is like the time direction, and this is like, well, we call that T or Y. I'm given these 3 points, and I want to fit them by a line, by the best straight line. So the problem is fit the point 1 is the first point. The second point is T equals 2, B equals 1. And the third point is T equals 3, B equals 2. So those are my 3 points. T equals, that's 2. So this is the point 1, 1. This is the point 2, 2, and that's the point 3, 2. And of course there is the line that goes through. So I'm looking for the best line. I'm looking for a line that probably goes somewhere, you think it goes somewhere like that? I didn't mean to make it go through that kind of won't.
Bro, that's crazy.
It will go between, so the error there, the error there, the error there.
We're getting to linear regression.
Small as I can get. Okay, what I'd like to do is find the matrix A, because once I found the matrix A, the formula will take over.
Wait. I need to check something. fuck? What the fuck is this? What the fuck is this, bro? Bump
So
club,
I'm
bro.
looking for this line. B is C plus DT. So this is in the homework that I sent out for today. Find the best line. So I'm looking for these numbers, C and D, that tell me the line, and I want them to be as close to going through those 3 points as I can get. I can't get exactly, so there's 3 equations to go through the 3 points. It will go exactly through that point. If, let's see, that first point has T equal to 1, so that would say C plus D equals 1. This is the 1, 1. The second point, T is 2, so C plus 2D should come out to equal 2. But I also want to get the third equation. And if that third equation, T is 3, so C plus 3D equals only 2.
Whatever, okay. Go on.
That's the key, is to write down what equations we would like to solve but can't. Reason, if we could solve them, that would mean that we could put a line through all 3 points. And we would like to solve but can't. Reason, if we could solve them, that would mean that we could put a line through all 3 points. And, of course, if these numbers 1, 2, 2 were different, we could do it. But with those numbers 1, 2, 2, we can't. So what is our equation AX equals B that we can't solve? I just want to say what's the matrix here, what's the unknown X, and what's the right hand side. So this is the matrix is
Okay, it's 2
1, 1,
by 3
1, 2,
matrix. Okay.
3. The unknown is C and D,
Mm-hmm.
and the right hand side is 1, 2, 2.
Yeah. Systems of equations,
I've
okay.
taken my equations and I've said what is AX and what is B.
Mm-hmm. Whoa, is that how... Is that how... Wait. So இப்படி தான் அந்த linear regression curve கண்டுபிடிக்கிறாங்களா? I mean, and the linear regression line is based on this shit?
Then,
Okay.
there's no solution. This is a typical case where I have 3 equations, 2 unknowns, no solution. But I'm still looking for the best solution. And the best solution is to solve not this equation AX equals B, which has no solution, but the equation that does have a solution, which was this one. So that's the equation to solve. That's the central equation of the subject. I can't solve AX equals B, but magically, when I multiply both sides by A transpose, I get an equation that I can solve, and its solution gives me X, the best projection, and I discover what the matrix that's behind it. Okay, so next time I'll complete an example, numerical example. Today was all letters, numbers next time. Thank you.
That was really cool. Love this, man. Projection and least squares. What is least squares? I need to do my research.
Welcome back, and let's write some more neat code.
Okay, bro, shut the fuck up. Shut the fuck up. Oh, it's the same thing? Bro, we're getting close. Close. Oh shit, it's the method, it's the underlying method of linear regression. Okay, linear regression. Oh shit. I'm getting into the good juice of it. Obviously, I think I need this one too. Fucking hell, that was good. That was the best one, I think. Let's look at this one. Bro, look at that. That's actually tough. Computer science and engineering, what the? That's like a graduate level course. Number theory, algebraic and so this is algebraic geometry, non-commutative algebra, commutative algebra, algebraic topology, algebraic geometry. Oh, we just have, okay. Fucking hell. That's higher education for you. Brutal. Brutal, brutal, brutal. I wanna see Gilbert Strang. Oh shit, he has like a. No fucking way, bro.
The fuck?
I do think like the way that I did is the right order, but fucking hell, I didn't know this existed. What is the prerequisite? It's undergraduate, right? Syllabus. Okay, I need to get. Okay, makes sense. Fair enough. Fair enough. Fair enough. What is the prerequisite for this shit? Bro, that's crazy. That's crazy. So, I have a linear algebra. Fuck. It's not, the learning is not over. It's just getting started. What else shit that he has? Shit. No. Bro, he has all of this shit? That's crazy. Are you crazy? Are you crazy, Mr. Gilbert Strang? Why are you so fucking smart? A vision for linear algebra. We have machine learning. That's crazy. I didn't know that. Okay, I'm gonna snap you. You're mine now. You're mine. Nah. 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 Networks. Bro, this is. Why is this fun? Why is this shit fun? And why did I do this beforehand? Okay, let's go back. Let's not get overzealous and lose ourselves in the process, gentlemen. Let this shit be in the background. We're gonna get to the good shit now. Before that, I need a break. OBS.
In 2013, when I was just
Let's go. Took like a little bit more break than I intended, but it is what it is. It is what it is, yeah. It is what it is. Should I? Yeah. Camera. Where's camera? Keepers. Okay, the break lasted for like 20 minutes. Fucking up. Okay, let's go. Linear regression or least squares. That's the topic at hand.
Okay, here's lecture 16, and if you remember, I ended up
best to worst, give a percentage. I don't need this. Fuck you.
the last lecture.
I don't need this. I don't need. Yeah, I don't need all of that. Might need different show.
Yesterday.
Okay. Just go on. Think that's fine.
With this formula for what I call the projection matrix. And maybe I could just recap for a minute. What is that magic formula doing? For example, it's supposed to produce a projection. If I multiply by a b, so I take p times b, I'm supposed to project that vector b to the nearest point in the column space. Okay, and one way to recap is to take the two extreme cases. Suppose the vector b is
12 to 16 courses, okay.
in the column space. Then
Cool.
what do I get when I apply the projection P? So I'm projecting into the column space, but I'm starting with a vector, in this case, that's already in the column.
What the fuck? Electives? So you like do other shit? Can I just learn math? Question mark, question mark? Yeah, I know all of this, okay. Bro. So retarded. What even is the fucking point? I don't get it. So retarded. Electives, general studies. I know my shit. It's like, if I want to learn about history, I'm gonna fucking do it. Know what I mean? Fucking retarded ass shit, bro. Let's get into this.
So of course, when I project it, I get B again, right? And I want to show you how that comes out of this formula. Let me do the other extreme. Suppose that vector is perpendicular to the column space.
Mhm.
So imagine this column space as a plane, and imagine B is sticking straight up perpendicular to it. What's the nearest point in the column space to B in that case? So what's the
Zero.
projection
Okay.
onto the plane, the
Straight
nearest
up.
point in the plane, if the vector B that I'm looking at is got no component in the column space, it's sticking completely 90 degrees with it, then
Zero.
PB should be 0. Right. So those are the two extreme cases. The average vector has a component P in the column space and a component perpendicular to it, and what the projection does is it kills.
இது வந்து இந்த சன் டயல்ல எனக்கு பார்த்துருந்தா தெரியும். சன் டைரக்டாக அடியில் இருக்கும்போது it shows
this
0.
part, and it preserves this part.
12 மணி,
Okay, can we just see why
basically.
that's true? Just that formula ought to work. Let me start with this one. What vectors are perpendicular to the column space? How do I see that I really get 0? I have to think, what does it mean for a vector B to be perpendicular to the column space? So if it's perpendicular to all the columns, then it's in some other space. We've got our four spaces. So the reason I do this is it's perfectly using what we know about our four spaces. What vectors are perpendicular to the column space? Those are the guys in the null space of A transpose, right? That's the first section of this chapter. That's the key geometry of these spaces. If I'm perpendicular to the column space, I'm in the null space of A transpose. Okay, so if I'm in the null space of A transpose, then I multiply this big formula times B. So now I'm getting PB. This is now the projection, PB. Do you see that I get 0? Of course I get 0. Right at the end there. A transpose B will give me 0 right away. So that's why that 0 is here. Because if I'm perpendicular to the column space, then I'm in the null space of A transpose, and A transpose B is zilch. Okay, what about the other possibility? How do I see that this formula gives me the right answer if B is in the column space? So what's the typical vector in the column space? It's a combination of the columns. How do I write a combination of the columns? So tell me, how would I write, your everyday vector that's in the column space? It would have the form A times some x, right? That's what's in the column space, A times something. That makes it a combination of the columns. So these B's were in the null space of A transpose. These guys in the column space, those B's are AX, right? If B is in the column space, then it has the form AX. I'm going to stick that on the quiz or the final for sure. That you have to realize, because we've said it like 1,000 times, that the things in the column space are vectors A times X. Okay, and you see what happens now if we use our formula? There's an A transpose A, gets canceled by its inverse. We're left with an A times X. So the result was AX, which was B. You see that it works? This is that whole business. Cancel, cancel, leaving AX, and AX was B. So that turned out to be B in this case. Okay, so geometrically, what we're seeing is we're taking a vector. We got the column space. And perpendicular to that is the null space of A transpose. And our typical vector B is out here. There's 0, so there's our typical vector B. And what we're doing is we're projecting it to P. And of course, at the same time, we're finding the other part of it, which is E. So the two pieces, the projection piece and the error piece, add up to the original B. Okay, that's like how our matrix does. So this is P.
Oh, that's a really good way to visualize it too. Why didn't I know that? It should have been, why didn't you say that before? So that's where the formula comes from. P is equal to BE. And that shit is AX, right? AX is equal to B minus E. And no, P is equal to AX, right? What am I missing? And E is what is E? E is like A transpose B minus E is equal to 0. I don't know where that formula came from. I'm thinking of something else.
P is AB. It's EB. It's the projection applied to B. And this one is, okay, that's a projection too. That's a projection down onto that space. What's a good formula for it? Suppose I ask you for the projection of the projection matrix onto this space, this perpendicular space. So if this projection was P, what's the projection that gives me E? It's, what I want is to get the rest of the vector, so it'll be just I minus P times D. That's a projection too. That's the projection onto the perpendicular space. Okay. So if P is a projection, I minus P is a projection. If P is symmetric, I minus P is symmetric. If P squared equals P, then I minus P squared equals I minus P. It's just, the algebra is only doing what your pictures is completely telling you. But the algebra leads to this expression. That expression for P, given a basis for the subspace, given the matrix A whose columns are a basis for our column space. Okay, that's recap because you need to see that formula more than once. And now can I pick up on using it? So now, it's like, let me do that again. I'll go right through a problem that I started at the end, which is find the best straight line.
Yeah, least squares, linear regression.
They weren't especially brilliant. T equal 1, 2, 3. Heights were 1, 2, and then 2 again. So their heights were that point, which makes it look like I've got a nice 45-degree line, but then the third point didn't lie on the line. And I wanted to find the best straight line. So I'm looking for this line, y equals c plus dt, and it's not going to go through all 3 points because no line goes through all 3 points. So I'm going to pick the best line, the best being the one that makes the overall error as small as I can make it. Now I have to tell you, what is that overall error? And because that determines what's the winning line. If we don't know, we have to decide what we mean by the error, and then we minimize, and we find the best C and D. Okay, so if I went through that point, I would solve the equation C plus D equals 1. Because at C equal to 1, I'd have C plus D.
I still don't get it. Is it like, okay, you went through that point, meaning is equal to 1. Okay, y is equal to 1. Okay, makes sense. It's still okay, y is equal to 1. dt
would come out right. If it went through this point, I'd have C plus 2D.
Oh, okay, makes sense. Y is equal to mx. mx plus c. What? Oh, that's the equation of the line. C plus dt. Okay, whatever.
Because at t equal to 2, I would like to get the answer. At the third point, I have c plus 3d, because c is 3, but the answer I'm shooting for is 2 again. So those are my three equations. And they don't have a solution. But they've got a best solution. And what do I mean by best solution? So let me take time out to remember what I'm talking about for best solution. So this is my equation, ax equals b. A is this matrix, 1, 1, 1, 1, 2, 3. X is I only have two unknowns, C and D, and B is my right-hand side, 1, 2, 3. Okay. No solution. With a 3 by 2 matrix, I do have two independent columns. So I do have a basis for the column space. Those two columns are independent, they're a basis for the column space, but the column space doesn't include that vector. So best possible in this, what would best possible mean? The way that comes out to linear equations is I want to minimize the sum of these. I'm going to make an error here. I'm going to make an error here. I'm going to make an error there. And I'm going to sum and square and add up those errors. So it's a sum of squares. It's a least squares solution I'm looking for. So those errors are the difference between ax and b. That's what I want to make small. And the way I'm measuring this is a vector, right? This is e1, e2, e3. Ax minus b. This is the e, the error vector. And small means its length. The length of that vector. That's what I'm going to try to minimize. And it's convenient to square. If I make something small, I make this is a never negative quantity, right? The length of that vector.
Usually, in like in any given set of linear equations, எப்படி இருக்கும்னு பார்த்தீங்கன்னா, it will be like this, right? But the minus e is like implicit, meaning it's like it's always going to be 0, right? But in certain cases, we need to find the least square where there isn't like a. In this case, there's like 3 variables, and there's only like. I mean, there's like 2 variables, and there's like. Well, 3 things. So you can't really like find it. So that's why the e is going to be much more visible, and we're finding the length. Apparently.
The length will be 0 exactly when I have the 0 vector here. That's exactly the case when I can solve exactly. B is in the column space, all great. But I'm not in that case now. I'm going to have an error vector, E. What's this error vector in my picture? I guess what I'm trying to say is there's 2 pictures of what's going on. There's 2 pictures of what's going on. One picture is in this is the 3 points and the line. And in that picture, what are the 3 errors? The 3 errors are what I missed by in this equation. So it's this little bit here, that vertical distance up to the line. There's 1, and there's C plus D, and it's that difference. Here's 2, and here's C plus 2D. So vertically, it's that distance. That little error there is E1. This little error here is E2. This little error coming up is E3. E3. And what's my overall error is E1 squared plus E2 squared plus E3 squared. That's what I'm trying to make small. Some statisticians, this is a big part of statistics. Fitting straight lines is a big part of science, and specifically statistics, where the right word to use would be regression. I'm doing regression here. Linear regression. And I'm using this sum of squares as the measure of error. Again, some statisticians would say, okay, I'll solve that problem because it's a clean problem. It leads to a beautiful linear system. But they would be a little careful about these squares. In this case, if one of these points was way off, suppose I had a measurement of t equals 0, that was way off. Well, would the best line be the same if I had this 4th point? Suppose I have this 4th data point. No, certainly the line would...
It would be like
it wouldn't
crazy.
Be the best line. Because that line would have a giant error, and when I squared it, it would be like way out of sight compared to the other. So this would be called by statisticians an outlier. And they would not be happy to see the whole problem turned topsy-turvy by this one outlier, which could be a mistake at first. So they wouldn't like maybe swearing. If there were outliers, they would want to identify them. Okay. I'm not going to... I'm taking I don't want to suggest that these squares isn't used. It's the most used. But it's not exclusively used because it's a little overcompensates for outliers because of that squaring. Okay, so suppose we don't have this guy. We just have these 3 equations. And I want to minimize this error. Okay.
Okay, we need to remember that least squares overcompensates for outliers. That's fucking sweet.
Now, what I said is there are 2 pictures to look at. One picture is this one. The 3 points, the best line, and the error. Now, on this picture, what are these points on the line? The points that are really on the line. So they're points, let me call them P1, P2, and P3. Those are 3 numbers. So this height is P1, this height is P2, this height is P3, and what are those guys? Suppose those were the 3 values instead of, there's B1, everybody's saying all these, sorry, my art is as usual not the greatest, but there's the given B1, the given B2, and the given B3. I promise not to put a single letter more on that picture. Okay, there's B1. P1 is the one on the line, and E1 is the distance between. And same at point 2, and same at point 3. Okay, so what's up? What's up with those P's? P1, P2, P3, what are they? They're the components. They lie on the line, right? They're the points which, if instead of 1, 2, 2, which were...
Are they getting projected onto the regression line? Is that what's happening?
the B's. Suppose I put P1, P2, P3 in here. I'll figure out in a minute what those numbers are, but I just want to get the picture of what I'm doing. If I put P1, P2, P3 in those three equations, what would be good about the three equations? I could solve it. A line goes through the P. So the P1, P2, P3 vector, that's in the column. That is a combination of these columns. It's the closest combination. It's this picture. See, I've got the two pictures. Like, here's the picture that shows the points. This is a picture in a blackboard plane. Here's a picture that's showing the vector. The vector B, which is, in this case, in this example, is the vector 1, 2, 2. The column space is, in this case, spanned by the, well, you see A there. The column space of the matrix 1, 1, 1, 1, 2, 3. And this picture shows the nearest point. There's that point P1, P2, P3, which I'm going to compute before the end of this hour, is the closest point in the column. Okay. Let me not, I don't dare leave it any longer. Can I just compute it now? So I want to compute, find P. All right, find P. Find X, which is CD. Find P and P. Okay, and I really should put these little hats on to remind myself that they're the estimated. The best line, not the perfect one. Okay. Okay, how do I proceed? Let's just run through the mechanics.
I think I can do it. Maybe not, but let's give it a try. Let's give it a try. What am I doing wrong? No. I'm not going to use this equation because it's not really perpendicular, is it? So P is equal to A hat and is that A? What the fuck is that? And I need to find bro, what the fuck is that diagram? Let's see how he does. I don't know.
What's the equation for X? The equation X hat. The equation for that is A transpose A, X hat equals A transpose A, A transpose B. The most, I will venture to call that the most important equation in statistics and in estimation. And wherever you've got error and noise, this is the estimate that you use first. Okay. Whenever you're fitting things by a few parameters, that's the equation to use. Okay, let's solve it. What is A transpose A? So I have to figure out what these matrices are. 1, 1, 1, 1, 2, 3, and 1, 1, 1, 1, 2, 3. That gives me some matrix. That gives me a matrix. What do I get a matrix to be symmetric? I expect it to be invertible. And near the end of the course, I'm going to say I expect it to be positive definite. That's a future fact about this crucial matrix A transpose A. Okay, and now let me figure A transpose B.
Oh, it has to be positive because it's a regression line, isn't it?
So can I tack on B as an extra column here? 1, 2, 2. And tack on the extra A transpose B looks like 5 and 1 and 4 and 6, 11.
Fucking
I think
pro.
my equations are 3C plus 6D equals 5, and 6D plus 6C plus 14D is 11. And I just, for safety, see if I did that right. 1, 1, 1 times 1, 2, 2 is 5. 1, 2, 3, that's 1, 4, and 6, 11. Looks good. These are my equations. That's they're called the normal equations. I'll just write that word down because it's... So I solved that for C and D. I would like to, before I solve them, could I do one thing that's just above here? I'd like to find these equations from calculus. I'd like to find them from this minimizer. So what's the first error? The first error is what I missed by in the first equation. C plus D minus 1 squared. And the second error is what I missed in the second equation, c plus 2d minus 2 squared. And the third error squared is c plus 3d minus 2 squared. That's my overall squared error that I'm trying to minimize. Okay, so how would you minimize that? Okay, linear algebra has given us the equations for the minimum. But we could use calculus too. That's a function of two variables, c and d, and we're looking for the minimum. So how do we find it? Directly from calculus? We take partial derivatives, right? We've got two variables, c and d. So take the partial derivative with respect to c and set it to 0, and you'll get that equation. Take the partial derivative with respect I'm not going to write it all out, you will. The partial derivative with respect to d, it's going to be linear. That's the beauty of these squares. Is that if I have the square of something, and I take its derivative, I get something linear. And this is what I get. So this is the derivative of the error with respect to c being 0, and this is the derivative of the error with respect to d being 0. Wherever you look, these equations keep coming. So now I guess I'm going to solve it. What will I do? I'll subtract. I'll do elimination, of course, because that's the only thing I know how to do. Two of these away from this would give me, let's see, 6. So would that be 2d's equals 1? Huh. So it wasn't, I was afraid these numbers were going to come out awful. But if I take two of those away from that equation, I get 2d equals 1. So I think d is a half, and c is whatever back substitution gives. 6d is 3. So 3c plus 3 is 5. I'm doing back substitution now, right? 3, can I do it in light letters? 3c plus, that 6d is 3 equals 5. So 3c is 2, so I think c is 2/3. 1/2 and 2/3. So the best line is the constant 2/3 plus 1/2 c. And is my picture more or less right? Let me copy that best line down again. 2/3 and a half. I'll put in the 2/3 and a half. Okay. So what's this P1? That's the value at t equal to 1. At t equal to 1, I have 2/3 plus a half, which is, what's that, 4, 6, and 3, 6. So P1, I promise not to write another thing on this. I'll erase P1 and I'll put 7, 6. Okay, and yeah, it's above 1, and E1 is 1, 6. Right, you see it all, right? What's P2? Okay, at the point t equal to 2, where's my line here? At t equal to 2, it's 2/3 plus 1, right? That's 5/3. 2/3, and P is 2, so that's 2/3 and 1 is 5/3. And that's sure enough, that's smaller than the exact 2. And then the final P3, when t is 3, what's 2/3 plus 3 halves? It's the same as 3 halves plus 2/3. It's, so maybe 4, 6, and 9, 6, maybe 13, 6. Okay.
13,
again,
6, yeah.
Oh, look at this. Okay. You have to admire the beauty of this answer. What's the first error? So here are the errors. E1, E2, and E3.
Yeah.
What was that first?
இப்போ இதெல்லாம் ஆட் பண்ணா we will get the sum of what will we actually get? இதெல்லாம் ஆட் பண்ணா the errors நம்ம ஆட் பண்ணா I think you'll get this. I'm not sure though. Not sure. Not putting mouths on my daddy's mouth. Pause.
Is error E1? Well, if we decide the error is coming up, then it's 1, 6. And the last error, 13, 6 minus the correct 2 is 1, 6 again. And what's this error in the middle? Let's see, the correct answer was 2, 2. And we got 5/3, and it's the other direction minus 1/3, minus 2 6. That's our error vector. In our other picture,
maybe not.
We just found P and E. E is this vector, 1, 6 minus 2, 6, 1, 6. And P is this guy. Well, maybe I've assigned the E wrong. I think I have. Let me fix it. Because I would like this 1, 6. I would like this plus the P to give the original B. I want P plus E.
So it is perpendicular. So meaning we have this shit aligned, right? We're drawing a. How is that perpendicular though? I don't get it. How is that perpendicular?
The match B. So I want minus a 6 plus 7, 6 to give the correct B equal 1. Okay. Now, okay, I'm going to take a deep breath here and ask, what do we know about this error vector P? You've seen now this whole problem works completely through, and I even think the numbers are right. So this P, so I'll write out what, if I can put it down here, B is P plus E.
Oh, it is
B
0.
P
Sorry.
was 1, 2, 2.
The addition of it will be 0.
The
Right?
nearest point had 7, 6, and the E. Okay, two vectors, vector P, and they're verified. Can I change 7 over the column space? So, vector, it's what everybody's saying. If I take the dot product with 1, 2, 3, I get minus 1 plus 4.
Yeah.
Never shows up. And the picture here for the best line. And it's the same picture. Just like this one's in the plane and it's showing the line. This one never did. For example of fitting by straight lines. So the whole C and D never shows up. And this is the two columns that give P. Okay. So that's least squares.
That is P minus C
most special, but most
in
important
an
example of fitting by straight lines.
linear.
So the homework that's coming then Wednesday asks you to fit by straight lines. So you're just going to end up solving the key equation. You're going to end up solving that key equation, and then P will be a x. That's it. Okay. Now, can I put in a little piece of linear algebra that I mentioned again, but I never did right. And I should do it right. It's about this matrix A transpose A. There. I was sure that matrix would be invertible. And of course, I wanted to be sure it was invertible because I planned to solve the system with that matrix. So, and I announced, like, before as the chapter was just starting, I announced that it would be invertible. But now, can I come back to that? Okay, so what I said was that if A has independent columns, then A transpose A is invertible. And I would like to first repeat that important fact, that that's the requirement that makes everything go here. It's this independent columns of A that guarantees everything goes through. And think why. Why does this matrix A transpose A, why is it invertible if the columns of A are independent? Okay, I guess I'm wondering, so if it wasn't invertible, then so I want to prove it. If it isn't invertible, then what? I want to follow that line of thinking and see what I come to. Suppose A transpose A x is 0. I'm trying to prove this is now two proofs. I don't like hammer away at too many proofs in this book, but this is like the central fact that it brings in all the stuff we know. Okay, so I'll start the proof. Suppose A transpose AX is 0. And I'm aiming to prove A transpose A is invertible. So what do I want to prove now? So I'm aiming to prove this fact. I'll use this, and I'm aiming to prove that this matrix is invertible. Okay, so if I suppose A transpose AX is 0, then what conclusion do I want to reach? I'd like to know that X must be 0. I want to show X must be 0. To show now, to prove X must be the 0. Is that right? That's what we worked in the previous chapter to understand. That a matrix was invertible when its null space is only the 0 vector. So that's what I want to show. How come, if A transpose AX is 0, how come X must be 0? What's going to be the reason? Actually, I have two ways to do it. Let me show you one way. This is, here, trick. Take the dot product of both sides with X. So I'll multiply both sides by X transpose. X transpose A transpose A, X equals 0. I shouldn't have written trick. That makes it sound like just a dumb idea. Brilliant idea. Okay. I'll just put idea. Okay. Now, I got to that equation, X transpose A, X equals 0, and I'm hoping you can see the right way to look at that equation.
என்ன பார்க்குறேன்னு எனக்கு தெரியல பாதி வாட்டி.
What can I conclude from that equation? That if I have X transpose A, well, what is X transpose A transpose AX? Is that, you see what it is?
That is A transpose. That's the same thing as that's permit. That is basically Is that not the same thing? I think so.
It's again going to be putting in parentheses. I'm looking at AX, and what am I seeing here? It's transpose. So I'm seeing here, this is AX transpose AX equaling 0. Now if AX transpose AX, so like, let's call it Y or something, if Y transpose Y is 0, what does that tell me? That the vector has to be 0, right? This is the length squared. That's the length of the vector AX squared. That's AX times AX. So I conclude that
Makes
AX has
sense.
to be 0.
Makes sense, yeah.
Well, I'm getting somewhere. Now that I know AX is 0, now I'm going to use my little hypothesis. Somewhere, every mathematician has to use a hypothesis, right? Now, if A has independent columns, and we're at the point where AX is 0, what does that tell us? That could be like a fill-in question on the final exam. If A has independent columns, and if AX equals 0, then what? Please say it. X is 0, right. Which was just what we wanted to prove. You see what that is? If AX equals 0, now here we use, this was the square of something. So I'll put in little parentheses the observation we made. That was a square, which is 0, so the thing has to be 0. Now we're using the hypothesis of independent columns, and that A has independent columns. If A has independent columns, this is telling me X is in its null space, and the only thing in the null space of such a matrix is the 0 vector. Okay, so that's the argument, and you see how it really used our understanding of independent. There's one case where the geometry gets even better. There's one case when columns are sure to be independent. And let me write that down, and that'll be the subject for next time. Columns are certainly independent, definitely independent. if they're perpendicular. Oh, I've got to rule out the zero column. Let me give them all length 1, so they can't be 0. If they are perpendicular unit vectors. Like the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those vectors are unit vectors. They're perpendicular, and they certainly are independent. And what's more, suppose they're, oh, that's so nice. I mean, what is A transpose A for that matrix? For the matrix with these 3 columns? It's the identity. So here's the key to the lecture that's coming. If we're dealing with perpendicular unit vectors, and the word for that will be ortho, I could have said orthogonal, but I said perpendicular. Ortho, and this unit vectors gets put in as the word normal. Orthonormal vectors. Those are the best columns to do that. Matrices whose columns are orthonormal. They're perpendicular to each other, and their unit vectors, well, they don't have to be those 3. Let me do a final example over here. How about one at an angle like that, and one at 90 degrees? That vector would be cos theta, sine theta, a unit vector. And this vector would be minus sine theta, plus theta. That is our absolute favorite pair of orthonormal vectors. They're both unit vectors, and they're perpendicular. That angle is 90 degrees. So, like our job next time is, first to see why orthonormal vectors are great, and
Trigonometry is gonna get.
then to make vectors orthonormal by picking the right basis. Okay, see ya.
It's gonna get mad.
In this video, we will discuss the orthogonal vectors and orthonormal vectors. Orthogonal vectors. If two vectors A and B are perpendicular to each other. That is, if the angle between the two vectors is 90 degrees. Then, the two vectors A and B are said to be orthogonal vectors.
I know
the dot
it.
product is equal. Pictures.
Okay, guys, I think that was underwhelming. That episode was underwhelming, bro. Don't know what to say. I got no 1, 2, 3, 4, 5, 6, 7 digits in my bank account. 7 more. And brother, what the fuck am I looking at? This is like a little bit smaller. But this thing though, that's my boy. Gilbert Strang, bro. My nigga. Yeah, where you at? Where you at? You got a fitty? Nigga. You know what I'm saying? Like, I used to be cringe. So cringe, in fact. Man, software is so cool. Hopefully, I want to make like a Tamil video on covering all of this. It's gonna be fun. I'm excited for that. It's gonna take a lot of time, but it is what it is, bro. Like, I want to give back to the community, you know what I'm saying? Like, you know what I'm saying? Like, give back to the community and shit. I'm being ironic. I don't talk like that. I don't talk like a thug. I don't talk like a black thug. That's irony.
Help. Is it MIT?
Important things about the course, plans for the course, and then
I can teach. I don't. It doesn't matter. If I want to teach, I can teach.
Minus 3t minus y is equal to y, derivative of the denominator.
Brother, we know this shit. This shit is easy, cuz. This shit is easy, cuz. Matrix method in data analysis, signal processing.
About my new course, 18065, and the new textbook, the new algebra and learning from data, and what's in those subjects. So they're really two essential topics.
I'm gonna finish the course. I might not even do this. I don't think I actually need to do this. Yeah, but once I finish this, write some tests, do some shit, I'm gonna be posting some videos on my channel. So stick around for it. It's like literally like no one watching, but listen, bro. One day some guy is gonna look at me and be like, "This guy fucking did it. He fucking did it." No stream. Yeah, I need to figure something